Hello, my young apprentice, and welcome to another episode where we are teaching you the dark side of the Force. This time we are taking a look under the hood of the system so that you can really write your own compiler extensions. And remember, in the last video we adjourned by saying we really want to write a recursive version of the factorial function, but the standard colon compiler does not allow us to do this because no forward references are allowed. So in this video we are learning enough details about the inner workings under the hood of the compiler and the interpreter, etc., and the internal structure of force words so that we can extend the compiler and make our recursive definitions a reality. And so if Lisp is, on the light side of the Force, then Force is definitely on the dark side of the Force, because it is really a double-sided sword. It will happily cut off your hand and your arm and everything else if you're not careful, almost like Darth Vader when he fought Luke Skywalker, right? And before you even notice, you turn yourself into Darth Vader. So let me be your emperor on this journey into the dark side of the Force, so that you can have full command and power over the Force. So I mentioned Lisp for a reason, because there are a number of similarities between Force and Lisp, and if you know Lisp, then learning and understanding Force might be easier for you. In my case it helped, right? So for starters, both Lisp and Force have a very small set of primitives, right? So the language cores are very small, and the rest of the languages are bootstrapped and defined in terms of these system primitives. So Lisp is largely defined in Lisp itself, and same for Force, right? Force is largely defined in Force itself. So even the colon compiler or the interpreter in Force is defined in Force itself, and this of course gives you the ability to change that easily within the language itself using the same language, right? The same holds true in Lisp, for example, for the listener or the REPL, right? The read eval print loop is usually defined in Lisp itself, and you can change it if you like, right? So that's a similarity there. Second similarity, I would say, both languages can use the same language both at compile time as well as at runtime, right? So in Force you can have Force words which, when executed at compile time, basically compute in Force itself the definition of the Force word that you are currently compiling, right? So it's literally Force words writing the definitions of other Force words, right? And in Lisp you have macros, and if macros are being executed at compile time, then they basically compute the functional definition of the function that you are currently compiling, right? So it's common Lisp macros, or basically computing the functional definitions of functions, and it's Force words computing the definition of Force words, right? So it's Force and Force again, and Lisp, and this meta-circular aspect, right? You don't find that in many other languages, and this of course makes the compiler and the languages extremely powerful and extendable, right? And flexible, and you don't have that in many other languages. For example, you don't have that in C. In C you have a preprocessor macro language, right? But it's not the same language, it's a different language, right? You're using there the preprocessor macro language, and it's much more primitive, right? It's not that full meta-circular cycle as you have it in Lisp and Force. And then the third similarity, in Lisp, everything is centered around the notion of a symbol, right? Symbols have value and function cells. And in Force, you have the word, and a word is, in that sense, similar to a Lisp symbol. It has a name, right? And it has code runtime semantics associated with it, right? So there's the CFA, the code field address, and then it can also have a parameter field of arbitrary length. The PFA, right, is a parameter field address. And we are going to take a closer look at the structure of these words in Force, because this is really what you need to understand in order to get an idea what's going on under the hood, right? All right, let's take a look at the structure of Force words now in more detail. Alright, let's try to understand words and their internal structure a little bit better. And we are going to use a colon compiler to define a new word. I'm calling it mult2, and all it does is it multiplies what's on the stack by 2. And I'm using dub to duplicate the topmost stack entry, right? And then I'm just invoking the addition, and then I'm printing the result. So just for demonstration purposes, of course, right? And I can invoke it by putting 3 on the stack, and then I'm executing my new word, and there I'm getting the result. And it doesn't leave anything on the stack for us, so the stack is empty after it got executed, right? So, and the colon compiler has defined this word mult2 now in memory for us, right? And we are going to have a look at the structure. And but the colon compiler is not the only force word that actually can create new words, but there are, for example, other defining force words, right, as those words are called. So words that are creating other words are called defining words, right? And variable is such another defining word, and it's defining a variable for us, right? Now A1 is known as a word to us which, behaves differently than a word that would have been defined by the colon compiler. So if I execute A1, which was declared as a variable now, all that does is it leaves the address of the variable on the stack. And why is that, right? Because now we can actually use the exclamation mark or set word in order to set and change the memory cell contents of the cell with that address, right? So if we want to store 1, 2, 3 in that variable, right, all we got to do is put the value we want to store there on the stack, then the variable, right, and the runtime semantics of that word is now, if it's being executed, it simply puts the address of its so-called parameter field on the stack, right, and then we can assign a value using the exclamation mark operator, right. Now this memory address has been changed, right, so the value is now 1, 2, 3, and in order to see that this is indeed the case, we are using the add operator to dereference the address and take a look at the value in that cell. So how are the words represented in memory, right? So we have defined 2 words. One was defined by the defining word variable. We have defined a variable called A1, and we have defined another word which was defined by the colon compiler, mult2, right? So words are really record-like data structures, and they start with a name field, right, which is just, the ASCII characters of the name of the word. It can be of up to 32 bytes, right? And after the name field, we have another field which is called the link field. And the link field basically contains a pointer to the previous word in the current dictionary, right? So the current dictionary contains basically all the words that are known in the dictionary, right? So basically what it is a pointer to the last defined word. And if the interpreter now looks for a word, right, is requested to execute, for example, A1, it basically goes to the last defined word, and it compares the name field, of course, with the requested word's name, right? And if it's not a match, then it uses the link field pointer to go to the previous word through the linked list until it finds the matching word, right? And that, of course, requires some time and is a linear search lookup, right? But eventually, if the word exists in the current dictionary, right, it finds basically the word, and then what it does is it executes the code field pointer, right? So at the code field address, we have basically a pointer, the code field, which points to a piece of code which does something, right? And each word has such a code field, and depending on the kind of word, there are different it points to different kinds of code blocks that do different things, right? The next field that each word has is the parameter field, right? And the parameter field can be of variable lengths. If the word is a variable, then it just contains the content of the variable, right? We stored 1, 2, 3 in there, right? And now you see what the piece of code actually does is when you are executing the runtime semantics of the variable, all that piece of code which is being executed, pointed to by the code field, right, does is it retrieves the parameter field address and puts that on the stack, right? So, but it does not do actually anything with the value in that cell, right? And I demonstrated that if you do A1, you actually get the address now of the PFA parameter field address on the stack. You need to dereference, get the value in that cell using the add operator, and then you are getting, 1, 2, 3, right? So this is how that works. And of course, you actually need the PFA and not the value, because you want to change the value with the exclamation mark or set word, right? And without the address, you can of course not, change the value of the variable. So this is how variables look like, right? The words, the variable words. But for the words that were defined by the colon compiler, that looks different now. So first of all, this piece of code is called the address interpreter, right? And why is it called like this? So basically, unlike the variable, which has the content here in the parameter field, in the parameter field of a word defined by the colon compiler, we now have the addresses of the definitions that make up that word, right? So remember that the first word that I was calling here, executing in the body, in the definition of mult2 was dub, right? To duplicate the topmost stack entry. So what the colon compiler has put into the parameter field of mult2 is actually the address, the CFA of the dub word, right? As the first entry. So yeah, this is what it has done. So at runtime, when we are executing mult2, the CFA, actually the address interpreter now goes through the parameter field and it actually executes what it finds in the parameter field, right? So at first it would execute dub by simply, calling it using its CFA, because the compiler has left the address there for us. And then when it returns, it, continues with the remaining fields in the parameter field until the definition has been completely executed, right? And remember that the next word that we are calling here was actually dot, right, for printing it out. So it was, it was actually plus, right? So the next address that is there in the parameter field is the address, the CFA of the plus operator, the plus word, which is then being executed. And next, we also did a dot, a print operation, right? Pop from stack and print. So this is what the colon compiler has left there. So you see, depending on the kind of word, we have different pieces of code pointed to by the code field, right? And if the word has been defined by the colon compiler, then this piece of code is known as the address interpreter, because it now goes through the PFA of the word and executes the addresses that it finds there. And of course, this is now much faster than the runtime interpreter, because it no longer requires the linear search through the dictionary in order to find the addresses of the CFAs of the words which are being executed, right? And for a variable, the parameter field simply contains the variable value, right? And the CFA piece of code only puts the PFA on the stack, but nothing else. Now that we know about the structure and internal representation of false words, and at least two different kinds of false words and their different representations, right? Namely variables as well as words that have been produced, created by the colon compiler, we can use that knowledge to do all kinds of funny things, right? So as explained, the runtime semantics of a variable word is simply it puts its PFA on the stack, right? So this is the address where the variable's value is stored, and we can use the set operator to change the content of that cell, right, like this. And we can use the add operator to peek into that memory cell and retrieve its value, right? And so, yeah. But this only works for variables, right? So how do you get, for example, the PFA of our colon compiler defined word might2, right? Because, you know, if you type it in like this, of course the compiler, the interpreter will simply execute the code behind it, right? And you're not getting, you know, anything on the stack. So if you want to get the PFA of a colon compiler defined word, there is a special operator or special word which is called tick, right? It's an apostrophe here, and with tick you can actually retrieve the PFA of any word, right? So for a variable, the PFA is of course, you know, exactly what you would get from executing the variable word directly in the interpreter, right? 61476 is again the same address, right? But now for a word defined by the colon compiler, such as might2, we can now also get the address of its first parameter field entry, its PFA, like this, right? And this is actually where the definition of the word starts, right? Remember that might2 starts with the dub word call, right? So at that address you actually have a call to the word dub, right? And then you might think, okay, so how about we simply execute, you know, what's now at that address and see what the program does, right? And we can try that. So first we put an argument on the stack, 3, and then we are getting the PFA of might2. And now, given that we have an address on the stack, we can use the execute word, which, you know, simply does a call, a jump to that routine and see what it does. It actually didn't work, right? So it didn't produce the output of might2. And why is this? So it's simple, because as I explained, you cannot execute the parameter field directly. Rather, there's a piece of code. What you have to execute is the CFA, right? And for a colon compiler defined word, the CFA contains a jump to the address interpreter, which then looks at the parameter field and executes the addresses stored there. So in order to do what we just tried, first let me clean up the stack again. You got to do the following. So you put an argument on the stack again, right? Then you are getting the PFA of might2. And now what you do is you are computing from the PFA the CFA. And basically all that is it subtracts 2 from the address that's now on the stack, right? If you remember the drawings, you know, in the structure of the words, you see that this is the PFA, the first cell, right? And if you go up, you know, to, because it's 16-bit addresses, right? If you go up to, then you actually get to the CFA, right? And this is all what CFA does. It's basically subtract 2 from the 16-bit value, right? And then with this address, we should be able to execute it now, because this then starts the address interpreter, which executes the parameter field definition of that word. And there you go. That worked, right? So, and remember that even for variables, there is a code field pointer pointing to some piece of code, right? And all that piece of code does for a variable word is it puts the PFA on the stack, right? And in the same way, you know, I can also invoke the CFA code, which is behind our variable. Again, we are getting the PFA, we are converting this into the CFA, right? And then we can execute this. And this doesn't crash, right? And you see that now on the stack we again have the same address of the PFA for the variable, right? 61476, which is of course the same as if I executed the variable directly. How about we verify that what I told you about the functioning of the colon compiler is really true? So let's have a look at the PFA of our word mild2, right? So if we retrieve the PFA of mild2, this now gives the address of the first word in the parameter field, right? And what we would expect to see at that address is a call to the CFA of dub, right? So we would expect the CFA of the dub word there. And let's simply have a look what we find at that address using the add operator, and then by popping and printing the 16-bit unsigned address. And you see that we are getting an address 9401. Now, how can we verify that this is indeed the CFA of dub? Well, as simple as that, right? So the same we do for dub. We get its PFA, right? And then the CFA. And then you see that this is indeed 9401. Now that we know the internal representation of the definition of a word in its parameter field, and we know that this is just, an array of addresses, basically, that gives us an interesting ability now. How about modifying this definition, right? So suppose we wanted to change, the call to plus here with a call to the multiply operation, right, to the multiply word. So in fact, instead of mild2, we would have basically a square operation now implemented, right? And it's, just memory, and it's simple to achieve, right? So all we have to do is we got to find out the CFA of the multiplication word, as simple as that, right? And we have that on the stack now. And now we are computing basically the address of the second entry in mild2's parameter field, right? So tick mild2, and we are simply adding 2 to this address, right? And now we simply replace this value stored there with our new address, right? The CFA of the multiply word. So, okay, let's see if that actually worked. Of course, we haven't renamed the word because we didn't change the name field, right? So it's still mild2. But you see that indeed by now it's now executing a square operation, right? Multiplied the word, the value on the stack with itself. So self-modifying code is incredibly easy enforced like this, right? And of course you have to be extremely careful as well, because one wrong address, right, and the whole system crashes, of course. Alright guys, this video is getting long again, and we still haven't accomplished what we had set out for today, namely extending the compiler so that we can finally write recursive definitions, right? So we're going to do this and in the next video. For now, one mystery remains, which I still want to explain and resolve before we wrap up with this video, and this is how are words actually being created, right? I explained that there are certain metrical words, force word defining words, right, as they are called, which have the power to create new words. And a variable is such a word, right? It creates a new word variable for us. And the colon compiler, of course, as demonstrated various times by now, also has the magical power to create new words, right? But, we cannot simply type in, a new word, because it gives us an error in the interpreter, right? So in order to create the word data structure that we discussed, we actually have to use the create word. And then this takes the name basically from the input stream to the right, because you couldn't use test as an argument on the stack, right, because it doesn't exist yet. So it has to read from the input stream. So similar to how tick works, right, it works by reading from the input stream to the right rather than from the stack. And this is how we would create our word, right? And this is the most basic word you can think of that doesn't even have a parameter field, right? But it works. Now it's defined, and you can also try executing it. So by retrieving its PFA, which actually points to, you know, a non-existent parameter field, but from there we can again retrieve, get compute the CFA by subtracting 2, and we can execute this, right? And since we have no PFA, actually, you see that what that does is it simply puts 0 on the stack. So this is basically a no-op, right? So in order to define a word which would have a parameter field that we could use, you know, for as a variable, for example, right? We can create a word using a lot. So the word test2 now has a parameter field of length 2, of 2 entries, right? So, and we put 2 on the stack, and then we are using a lot. And now we actually have a PFA of size 2, right? And we can use this to store information there. So if we wanted to retrieve the PFA of test2, that's now a very defined operation, right? And this is where the the parameter field starts, right? So this is how words are being created, and both variable and the colon compiler internally behind the scenes are using create to create new words, right? So one mystery solved. The last thing that I would like to explain in this video is how to actually define defining words, right? And a good example for a defining word, which we haven't seen yet, is a constant, right? So we have seen a variable and we have seen the colon compiler. All these words basically have the ability to define new words, and they are called defining words for that reason, right? And constant is also a defining word, and it's a bit different from variable, right? So unlike variable, you also supply the value of the constant at the time you are creating it, right? So here we are defining a constant C1 with a value 1, 2, 3, right? And if we now execute our constant C1, if we execute our word, what the CFA behind this word does is it basically retrieves the value from the parameter field of the word C1 and puts that on the stack, right? So, and this is of course a bit different from a variable, whereas for a variable, if you execute it, you are getting the PFA on the stack because you would need that if you were to change the value of the variable. For a constant, this is of course not necessary and indeed unwanted, because the constant, you know, you're not supposed to change the value, right? So, and the power of force is that you can now define your own defining words, right? And suppose we wouldn't have constant already defined, so we indeed have the ability to define our own def constant defining words, right? And we are using the colon compiler for this. Let's call our version of constant def con, right? And what it does is, you know, when it's being executed in the form defcon C1 or C2, right? C1 is already defined. We are first executing create. What create does is now at execution time of defcon, it reads from the input stream the supplied word name, right? And it finds C2, right? So it creates C2. This argument is now implicit from the input stream, right? I don't need to put it here. And what we now can do is, you know, since we also already have the value for our new constant on the stack, when the word is being, you know, executed, the defining word is being executed, we can use a new operator to retrieve, to pop that value, the constant's value from the stack, and compile it into the PFA field of the newly defined, of the newly created word C2, right? And this is what the comma operator does. So it gets a value from the stack and it compiles it into the next available dictionary location, as we would say, or PFA PF parameter field location in the newly created word C2 in this case, right? Our constant word that we are defining. Now our new constant is defined, but if we are now executing this constant at runtime, how do we actually get the value, from the PFA on the stack? And for this, a special construct is now being used, and this is new. This is does, right? Greater than. So it's a special construct, and it basically now is used to define and specify the runtime semantics of each new word which was defined with defcon, right? With our new defining word. So at that point, when the word is being executed, C2, right? We at that point have the PFA of the word on the stack, and all we got to do now is basically retrieve the value, right? Using the add operator, and now we have the value of the PFA, the first entry of the parameter field on the stack, which is of course the value of the constant, right? Now in order to make it a little bit more interesting, we can also maybe print something on the screen. So we duplicate that value, because we can then also print it, right? And then maybe let's have an output and say first we want to print the value itself using dot, right? And then we would also want to put some text behind it like const, right? So that would behave a little bit different than the standard constant, right? So just to make it more interesting. And now C1 was defined with the built-in constant, right? And I showed you how that works. And now we are defining our constant C2 using our new defcon defining word, right? Like this. And okay, it's defined. But now look what happens if we execute it, right? Because we specified a different runtime semantics, we now expect, in addition to finding the value on the stack, we also expect that, it's being printed right away, and also constant, as specified in the CFA, basically, the runtime semantics that we specified using does for that word works as expected, right? Whereas this is of course simple output, but we also have the value on the stack. So you see how powerful that language is, right? So you can define, your own defining words. And a little bit more complex example could be, for example, you want to define a defining word like def point, right? Or def pair. And what that does is, it puts basically, it represents a pair or a point of xy coordinates, right, in a constant. And when you execute such a instance, a word of that new data type point or pair, you would find two values on the stack for the first and second component, or for the x and y coordinate of that point, right? So let's define another defining word, and we call it def point, right? And it does the same thing. It creates a new word, but this time we are compiling now two arguments from the stack into the parameter field of the freshly created word, right? Using comma, and then the does runtime semantics is also a little bit different, right? So remember now, we start with the PFA of the word which we are executing, right, of the point instance. And now we have two parameter field entries, and we are going to retrieve the values, and we are putting them on the stack, right? Since we need to retrieve two values, right, we duplicate the PFA because we are going to consume it, right? We are then going to the second entry in the parameter field by simply adding 2, and then we can retrieve now the y coordinate, right? And we can now not directly retrieve the x coordinate, because currently we have the y coordinate on top of the stack, so that would, since this is not an address, this wouldn't be defined, right? But since we duplicated the address, we can now swap, and now we have an address again on top of the stack, and we can retrieve the x coordinate. And now they are in reverse order. Now we have yx on the stack, right? So let's bring it into the xy order by swapping them again. And this is what that point, the semantics, the runtime semantics of a point instance would be, right? So, okay, let's create a point. We supply the two arguments, x and y coordinates, right? And then we are using def point p1. Okay, so p1 is defined now. Let's have a look at the stack. So stack is empty. And now let's execute p1. And what do we find on the stack? There you go. Now let's have another one. 5, 6. Def point p2. Stack is empty. p2. And 6 and 5 on the stack, or if we pop them in reverse order, we first pop x and then we pop y. Yeah, great, right? So this is a very powerful language. So the ability to define your own defining words is the first step towards, basically extending the compiler and really tailoring and customizing the language for your problem at hand. So this is how you would, for example, define your own user-defined data types, right? And I think you got the ideas. All right, guys. So so much for this video, and more about finally recursive definitions in the next video. But now we really have all the basic knowledge of the internals, that's really required in order to understand what's going on. And we can, in the next video, finally wrap that up. Until then, thanks for watching. Bye.